Hey, John here. Let's take a look at how I implemented the video display RAM in my implementation of the VDP from Texas Instruments, the TI-9118, described in this manual here. If you've seen my channel, you've seen me look at this before when we use the real deal actual chip in my Z80 Retro series. And this section of the manual right here is the part that we're going to focus on today and how we access the video memory, how you read and write the VRAM in the chip. Big thanks to everybody that supports my channel, especially the VIP patrons listed here. Thank you very much. See the links in the description below this video if you want to support this channel, even if it's a like and a subscribe. I appreciate it. Thank you very much. All right, I'm going to jump around a little bit here maybe. Let's start with this block diagram. Now, I drew this up when I first started working on my implementation of the VDP, the TI-99 chip, when I tried to decide how I was going to make everything work. So what we've discussed so far, if you look at this diagram, this is the CPU interface over here. Pardon this high quality CAD drawing, but this is what I got to work with. This is a hobby. I don't always like to transcribe all this into perfect doc. If anybody wants to do that and donate it to the GitHub repo, feel free to reach out and let me know in the GitHub repo for the code that you're going to see here today. That'll be in the description on YouTube as well. Thank you in advance. Anyway, so the CPU has a clock domain crossing bit of logic here. We talked about that in the past, and it uses it to access the VDP registers here. We talked about that in my channel in the past as well. Today, we're going to just talk about the VRAM here and look ahead a little bit. The VRAM is accessed by this counter down here. Now, we'll take a look at the VDP doc in a second, just to recap how this whole thing works. The short of it is the CPU doesn't just simply throw over an address and then say, here, I want to read data from that address, and then pow, it gets it back. It's not a regular RAM like the main memory of the Nouveau or Z80 style bus, because the address used comes from a counter down here that the CPU can set a very much the same protocol that it uses to write values into these control and configuration registers that we already talked about. So you're going to see a very similar kind of a state machine that's used to let the CPU say, here, I want to store some address value into this counter down here, and then subsequently that counter will be used to supply the address. That'll be used if the CPU wants to read a byte, it'll get it from the address in the counter. Every time it reads a byte, the counter will be advanced by 1 so that it can just keep reading and reading and reading, and it'll just walk through memory and get 1 byte at a time from successive addresses. Same thing is true for writing. It writes down here that we use the same counter. As far as I know, I believe that the VDP, the TI-99 family, right? The 99, 18, 91, 18, all the different variants. I think they have a single counter that they use for both reading and writing. And that's how I've implemented it here. If I'm wrong, let me know in the comments below. We can always change it and use 2 separate counters, one for reading and one for writing. I've seen notes on the internet about that and how that's a shortcoming with the design, but I want to be compatible, so that's what I did here. So the short of it is, the CPU can set up an address in this counter and then subsequently use the counter for constantly, repeatedly writing bytes into memory 1 at a time, or reading bytes out of the memory 1 at a time through this path down here. I'll talk about this mux and this other path down here when we talk about the finite state machine that I drew as a cloud over here that operates all these other latches and muxes over here, which is used to read the pattern table and the name table and the color table and generate the pixels 1 at a time. Okay, so we're working in this direction. The video out in this diagram, by the way, comes from right here. If you want to follow that, if you want to look ahead on how that's going to work. This diagram is held true pretty much over my whole design. So I got a pretty close estimate on how this thing's supposed to work. What you don't yet see in here are these sprites. These are not part of this diagram, and I'm still working on that at the time that I'm recording this video. But what'll happen down here ultimately is that it's a sprite like the pattern base and the attribute base or whatever. The registers 5 and 6 have to do with more different ways to address the memory is the short of it. So they'll end up running into this box, and the state machine will be used to access the sprite pixel data, just like it does now when it accesses the regular character data. Okay, and we'll go over all that in down the road after we get the basics. First thing we need to do is understand how the darn memory is going to work. Okay, so here's a zoom into that manual we just saw the cover of. Right, this is like the 9118 and family VDP documentation here. Right, so what do we got? If we want to store data in the VDP registers, I got a video on that. Look at the playlist that includes this video. There'll be a link in the description below the video on YouTube. And we have this like two-state thing, and we do a mode 1 write. I talk about all that fun stuff in the other video and in the whole series when we're using the VDP on the Z80 Retro project. So I'm not going to repeat that here. The short of it is that you would write a data byte, and then you'd say, here's the register I want to store that byte into, and a double whammy kind of a thing in order to store data into each of these 7 registers. Okay, so each one of these is a double write operation to pick the register and to provide the data. Okay, and those are write-only registers. You can't really read it back. Now, when you write a data into the register in mode 1, you have this requirement to set the most significant bits of the second byte that you send out in the double whammy. You have a 1 and a 0 here. Okay, that's a requirement, and the reason that's a requirement is because of what we're about to see when we're accessing the VRAM. Basically, you do a double whammy, but you have a different code up here. So this 1 0 up here means that I am in this second byte that's sent to the VDP in mode 1 is an address within which you're supposed to store this data for the register. Okay, down here, if we want to write into the VRAM, look closely here. The second byte has a 01, and if I'm going to write into the VRAM, now if I'm going to read, notice we got a 00 in there. So these 2 bits here are kind of like a command, is what I'm sort of thinking. So I view it as a command. If it's a 1 0, I'm going to store this previous byte 1 into a register. If it's a 00, I'm going to store this and this into this address counter, which is drawn in this box down here, which holds the address that is used for subsequent reading and writing to the video RAM. Okay. Now they give you a little bit of a bullet list here. What do you do if I want to write into VRAM? Send the lower 8 bits of the address that I want to write into the VDP with mode of 1. I'm going to write mode 1. This is the least significant byte of the address. Okay, and remember TI numbers their stuff backwards. So that's the low byte. The second byte is an 01 followed by the rest of the bits. You don't have 64K, you only have 16K, so these 2 bits aren't used in the address. So this is the most significant whatever you got here, the most significant 6 bits of the address, okay? That is how you get a value into this counter. Once the counter has an address that you know what it is, you can then write a byte. All you want in mode 0, bang, bang, bang. You just keep on writing bytes in with mode 0 selected here. Remember, the mode is kind of an address bit on the VDP chip. So it has like 2 different IO addresses. And so this is basically A0 coming from your Z80. So when you're repeatedly writing these data bytes out here, it'll go, the first one will go into the address that's you downloaded in mode 1 here, okay? And that's kind of written out here. The low bits, the upper bits, and the 0 and 1 up here for the kind of like the command. Then you write a byte, mode low, that's mode 0. right? More bytes, bang, 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 bang. Okay, so these bytes, every time you write a byte into the VRAM, it will advance this counter by 1, all right? So there's the big picture here. Now, what we need to do, and by the way, the same holds true for reading. You send the address, and then you just continuously read instead of continuously write, and the reading happens in both 0, okay? Now, get these out of the way. Remember what we have to work with. I'm using an ICE 40 FPGA in my project I'm working on here. And this manual here is the Silicon Blue Ice Tech. If you watch my channel, you've seen this before. You don't really need to get so much into this. I just wanted to say, here's the authoritative source, and base what I'm about to tell you as fact is in fact a fact, okay? So the bottom line is, it says the ICE architecture supports dual-ported synchronous RAM. Synchronous meaning that if I want to read or write to this thing, it has to happen on a clock edge. It's not an asynchronous RAM like the regular memory we use in, Z80 regular old, retro designs, where you've got a read and a write address and a chip enable and stuff like that, where the chip just simply emits data as soon as it's enabled. The way this thing works is you enable the chip and then you give it a clock edge. I think the diagram, well, really simple diagram down here. This is your clock. You have a clock enable and a write enable. Not sure why you need both of these, because if you can't clock it, you can't write it. Same with reading. It might mean that if you disable the clock, maybe it saves power or something like that. I don't know. Let me know in the comments below if you know the difference between these two. Maybe it gets into it in the narrative somewhere in here. I don't know. Anyway, bottom line is we have 2 ports. Now, it says it's dual ported, but it's not really. It has a port that's write only and another port that's read only. So, yes, it has 2 ports. However, it's not dual ported in that I can do anything I want with each of these 2 ports, like read from both of the ports at the same time or something like that. No, it's just write only on one port and read only on another port. The way this works is I have a separate address for writing and a separate address for reading, separate clock for reading, separate clock for writing. Right now, we don't care so much about the separate clocks because this is all in one clock domain, and we'll see in a minute that this whole thing exists in the VDP part of the design that we're going to look at. And the write side of these are going to become part of, this is the actual memory blocks that the FPGA has, but we're going to use an inferred memory to create it. And the reason we want to look at this thing first is while Verilog is smart enough, Yosis, this is the compiler we're using, it's smart enough to know how to infer a memory, but only if we use it right. We have to use it in a way that's compatible with this block or it won't work. It'll just, no. Okay? Short of it is, we need to make sure we use it synchronously, and it tells you down here. You can have positive going read clock, edge, and a positive going edge for your write clock. This is actually how we're going to use it. You can also have them on different edges and stuff if you want. Bottom line, you have a write port separate from a read port. Anything you want on either side at any time. We're going to use the same clock for both, and we're going to have writing only on one side, reading on the other. Now, if you think about it, we have what we'd like to have are 3 ports, because the CPU needs to be able to write into the memory as well as read from the memory. And we haven't gotten into the nitty-gritty yet, but the finite state machine that's running needs to be able to read the colors and the patterns and all that fun stuff, okay? So we have 2 different readers that have to sometimes read at the same time, or somehow we got to synchronize all that, and I'll show you how that's going to work because that's our only option. We have 2 readers, and we only have 1 port that allows us to read. We have a single writer, so we don't care so much about the writing. The writing, we'll just let it go. Whenever the CPU wants to write, bang, we'll write into it. But reading, we need to be careful. So the details of reading is going to be, we'll talk a little bit about it here, and then we'll talk about the rest when we go over the finite state machine, because finite state machine The short of it is, you'll see here, is this has to run at the pixel clock speed for the video. It can never stall. You can't put a wait state or anything in it. No, it has to get what it wants when it wants it. So what we're going to see in the memory in my VRAM implementation is kind of a priority access read that the FSM, the state machine here, can assert whenever it wants. It'll take precedence over if the CPU wants to read, okay? And I'm going to do it in such a way that neither of these ever has to block, okay? Short of it is that as long as the finite state machine doesn't hog access to the memory, we can kind of time share and interleave access to this, okay? The details we'll see in another video. But we need to build our memory. Our VRAM module has to deal with the fact that I've got two readers, one writer. I've got this clock, this counter that runs every time the CPU writes a byte or reads a byte. I need to advance to the next address down here, and you're going to have to see some sort of priority logic in my implementation as well, in two different ways that reading will take place. Okay, so there's all your foreshadowing. Give us a nice, what do you want to call it, your context for what we're going to look at here. So here's my VRAM module. This is part of the Z80 project. Again, the GitHub link will be below the video. I'm in the FPGA/VDP 99 subdirectory. And here's the module here, okay? You read this in the manual we were just looking at. I pasted a summary of it in there. How do you write? You write the low byte of the address in mode 1. You write the high byte of the address in mode 1 with this in the most significant 2 bits, and then you can just continue writing. Reading is the same way, except the pattern's different, and then you repeatedly read to get all the subsequent bytes. Here's a note about this priority DMA access. I decided to call it, I probably should have called it FSM and CPU so that would make more sense, but this evolved into what it is. I'm sorry. Maybe in another version I'll clean up my naming. I don't know. In any event, the short of it is here that I note that DMA read tick, this is the thing that the FSM can assert if it wants to use this cycle to access the memory and read something that it needs, like a bit pattern or a color, something out of the color table or something like that, okay? So DMA read takes precedence over the regular old read, and it is assumed that, and this is critical, coordinating these signals is a task at a higher level, all right? So this doesn't care if the state machine hogs access to the memory and starves the CPU. That's up to the other modules. And this thing, we've seen this before, is instantiated in the VDP 99 module. Not the top level module, the whole design, but the top level module for the VDP section of the Nouveau project. As we've seen, at least discussed in the Discord, the VRAM size is configurable in here, and the amount of memory that you can use on the ICE 40 chip that we're using, the HX4K, it only has 16K of RAM, and we want all 16K to be used for video RAM, but we need it for other purposes. So for the time being, we either can run with, less memory. I mean, the VDP is designed to support either 4K or 16K. Mine can allow as much or as little as you want. I think I run it in my test version that I build into the Project Nouveau right now as around 12K or maybe 13K, as much as I can, modulo the other memory needed for like the boot ROM image and stuff like that. That's in the same project, okay? So you'll see this is overridden quite normally. It doesn't usually run with 8K, but it may in the test case that we build, okay? Here's the usual ports. We've got a reset, a clock, a read, and a write tick. We've seen these before in my design. These are the CPU read and write signals that have been transferred and synchronized into the VDP clock domain. This is the mode bit. This is the least significant bit of the address normally. So this is the address. Am I using the address setup mode for like the register or the VRAM we just saw with the other manual with the mode 1 writes to configure the address for the VRAM and stuff like that. And when we're in mode 0, that's when we're reading or writing data in and out of the VRAM from this module here, okay? These two signals we're going to use for the finite state machine, and the if the finite state machine wants to access the video RAM, what it's going to do is it's going to send an address here. It's going to reach right in here and say, hey, I want you to read from this address right now when this tick goes true. And remember, the tick signals are single period signals that exist for the duration of one of these clock periods up here. And this clock runs at 25 megahertz, which is really the VGA clock speed. But we also use that to run our VDP. It's running twice as fast as the pixel clock that comes out of the VDP. It's really running. The VDP generates 12.5 million pixels a second, but the VGA runs twice as fast. So what we're really doing is you're seeing two VDP pixels, or rather I should say two VGA pixels, represent one VDP pixel. Okay, so keep in mind that this clock is, when we start looking at the finite state machine, you'll see there's some logic over there where it'll use every other clock cycle to update the pixel on the screen, because the VGA wants to run twice as fast as the TI 9118 does when you're mapping the pixels onto the screen in VGA mode. Okay, so this gives it priority access with an address from the state machine. And we'll talk about that later. The data that we're writing into this VRAM block, not necessarily into the VRAM, because remember, when we're doing these mode 1 writes, the address, the most significant and least significant bytes of the address show up on the DIN port here. And then if you start writing data into the VRAM, then yes, the DIN will hold the data that gets written into the VRAM as well. So this kind of has a dual purpose. The D out here is always the data that comes out of the VRAM. If you use read tick from the CPU, it means, as you saw on the VDP doc, it comes from the address counter register, which is actually right here. The adder reg is my counter register in this module, and if you go back to our block diagram, that's this box right here. That's adder reg, okay? It's being used to represent the address of the VRAM that we want to read from or write into, okay? And that's where this would come from if we're using a read tick. Otherwise, if we're using a DMA read tick, then we use the DMA address, represents the address where the data would come from. Okay, so let's look at our state machine. It's pretty straightforward, and we've looked at the register access implementation already. You're going to see a very similar result here. This code is a different style, but you still have this two-step state machine, as you saw, that we need in order to get through this part of the configuration to prepare for reading or writing. You got this double write into mode 1 to get the thing configured, followed by then, when we're dealing with the VRAM, repeated writing or repeated reading. Okay, so here's the inferred memory. Very simple, very subtle. Maybe I should put a comment over here. This is the actual VRAM memory. That's redundant since M stands for memory, but I think you know what I mean, right? Okay, so what do we got here? We've got the usual kind of stuff going on here with some registers that we create with a state machine down here, with a combinational logic we'll write into here, and then the sequential logic will update these at the edges of the clock, which you see right in here. Okay, you've seen this on my channel 100 times, or a dozen or two maybe, if not 100, a half 100. Okay, the dout reg will get assigned the value, which you see right here, that comes out of the VRAM if and when it is actually read. And then it is propagated to the port in this assignment statement up here. And I've mentioned this before. I usually make my ports wires, and then in my code I have a reg in here, which means I got this one extra thing. I've talked about this before. You could have just made this a reg and wrote directly to dout instead of this dout reg thing. The reason I do this is because when you're debugging, you want to leave the ports alone, and you might want to change what and how and why gets assigned to them. So I find it convenient to just make all these wires and then kind of shadow them with a reg down here and do this. When you're done debugging, this looks a little bit redundant, or it can anyway, but you know, it keeps things simple and easy to hack. Otherwise you start adding a reg in order to hold something to stage it, or put a complex expression in here that you can then not assign to a reg because you're not in an always block, blah, 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 blah. I talked about this before, okay? So that's why that's simplistic and seems redundant up there. Just a reminder. This thing here is what is doing the reading and the writing of the actual memory. Remember, we have to transfer data to an inferred block RAM on an edge. So on a pause edge of the clock is the only time I move data into or out of the VRAM. And notice I'm doing both at the same time in here, which is fine because it's dual ported. So the short of it is what? dout reg on every pause edge of a clock. There's no if or anything in here. I mean, arguably this is an if, but no matter what, dout reg is always read on every single one of these clocks. What gets, well, it gets written into the VRAM as read, I should say, on every pause edge of the clock. What's it reading from? Well, if the read tick is true, and that means that the state machine needs something and it needs it right now, and it needs to know a byte, like I said earlier, from the VRAM address given here, then do that. If it's not hogging access to the VRAM right now, then use the address reg counter register that represents the address that the CPU needs to read from. If it wants to read from the memory, that is what it wants to see. Okay? Now think about this for a minute. It's always reading the VRAM. If there's a priority access, it reaches in there to grab the priority value and sends it back, presumably because the state machine needs to read right now. Whenever the state machine is not wanting to grab priority access to the VRAM, we gratuitously read whatever the current address register value has in it, because the CPU might subsequently want to know what that value is. This gratuitous reading is why we always have a value ready, potentially have a value ready for the CPU to consume if it wants to reach in here and grab something at any point in time. We'll see when we look at the rest of the code, the state machine and another mux thingy that I put together. What we do is we always read from the memory and we cache the output value when we're not doing a high priority state machine access. Okay? Whenever we read from the address counter, and we do it before the CPU even asks, we store it in our registers elsewhere, we will see, so that we have it handy should the CPU ever need access, okay? After which we advance this address. We'll see that logic down below here in the combo circuit of our state machine. So this is what's happening in that one line of code there, all right? So there's some subtlety there. Keep that in mind. If you get confused, back the video up to this section and look at it again. So what happens here? Well, if the CPU ever wants to write in mode 0, that's the only time we're allowed to write in a VRAM. It's down here. It means that the CPU has to have already set up the memory address counter. And if it doesn't, then, I mean, arguably, who cares? Then he's writing to some unknown location. It still works. Okay? Try it on a VDP. On the real chip, I'm sure it'll work there too. It's not going to like not do it. There's always going to be garbage in your address register, even if you don't write it yourself. It might start at 0, it might start at garbage, or in this case, it'll be either 0 or it'll start where you last left off. Okay, so anyway, the short of it is, you only want to write into the VRAM whatever's on the DIN signal, if the CPU really wants to do it, okay? You don't want to write garbage in. You can always read garbage out of the memory. You can gratuitously read in advance, even if nobody wants to consume it. That's okay. But you'd never want to gratuitously write junk into a memory. So that's why there's an extra guard on this that you don't see up here. This one's in, if and only if we're in mode 0, do we take the data and we put it into the VRAM. There's no extra special stuff like this going on because the state machine never writes into the memory. So anytime the CPU wants to write, we can do it right away. That's what's happening right here. But of course, only if it asks to do it. Then we get down here to the state machine. Take a look at this comment up here to make sure we're good. If we reset, oh yes, yes, yes. I think we talked about this when we talked about the registers. One of the problems with the design of the TI 9118, that family of these processors, what happens if you write a byte 1 and then your program crashes? And then you start your program back up and it comes along and says, ooh, I need to set up something and I want to write it in the VRAM. So it sends another byte 1. Well, the VDP is waiting for byte 2, not byte 1. And if coincidentally the top 2 bits look like this, the first thing you write into looks like the last half of the address, then your code would be writing its byte 2, and then this VDP would take it as a data. It would be out of whack the whole time. The whole thing would be a disaster area. So the designers decided, rather than doing something, in my opinion, that they should have, like build a way to definitively set the state of this thing, what they did is they say, if you ever read from the status register, it will reset the state that's flipping back and forth, waiting for byte 1 versus byte 2. The idea that I want a 1 byte, then another byte, we got to keep track of that in our code. And we have a 1-bit value that says I'm in state waiting for the least significant byte, or I'm in a state waiting for the most significant byte. You're always going to either be waiting for one of those 2 values when there's a mode 1 write access going on to the VDP. Same is true for the configuration registers. That has the same problem. What if you write an in that case, it's a data byte. It's up here, right? You're writing a data byte in mode 1, followed by the register select. Well, what if you write a data byte and you crash, and then you come back and you write another? Same thing. You got this 2-byte whammy thing, and if you don't write both bytes, the whole thing gets out of whack and it'll stay stuck, and there's no way to know for the CPU to figure out that this is going on. So somewhere buried in this doc, it says, if you ever read from the status register, what it will do is it'll say, I don't care what I was doing. I will reset my logic for the accessing the VDP registers and the VRAM so that the next mode 1 access, I should say the next mode 1 write access, will be to expect byte 1 for either a VDP register write or to configure the VRAM for transfer, okay? So we see a little bit of that in here. We saw that in the VDP register thing as well, and I call that a phase error, right? Because if you get out of phase, you're 180 degrees out of phase. VDP wants a second byte, but you think it's time for you to write the first byte. It'll just always be wrong, and nothing good can come of it. So the short of it is, if you ever have a an access to the status register, we need to make sure that we reset our state machine in here, okay? And that's what's happening right here, by the way. Whenever you're reading in mode 1, it's the only way you can read this status register up here. Mode 1, read. This thing will reset our state thingy here, okay? And state next is either a 0 or a 1. When it's 0, it's waiting for the first byte. When it's 1, we're waiting for the second byte, and we can see that right down here, okay? So that's what this is doing. Otherwise, it's like, what? All right? And it's the only way a program can knowingly get the things back in sync if it comes up in an unknown state. And arguably, when you're dealing with chips like this, you're always in an unknown state when your program starts. So you got to like smack it upside the head to get it synchronized, and then you're off to the races. The other thing about this that's really annoying, and why I said they really should have done this another way, is if you have interrupts enabled and you go into an interrupt handler and you decide, I want to read the status register, which is the only sane way to do this on our real TI-99 due to timing and other, metastability problems that I've talked about on my channel in the past. The short of it is, you're damned if you do, you're damned if you don't. This thing is a pain in the butt. You need to make real sure that you're not in the middle of doing this while you're getting an interrupt in between here. Otherwise, every time you get an interrupt, you could come back to your program and be broken, okay? So this is annoying, but we need it for compatibility. So, the short of it is, I usually don't enable interrupts when I mess with this thing. You can, but you need to make real sure that when you're accessing the VRAM, that you do it after an interrupt occurs and get all your work done before the next interrupt occurs. And you can do that by timing your code and just being careful, which is, to me, a really crappy thing to have to do. But it's the era that we were in, and I think it was short-sighted. It's probably a design flaw in the chip. They should have had another way to do the resetting that was independent of just every time I get an interrupt, I'm going to screw up the status of the machine. Not a good idea. I digress. Okay, so here's the combo part of the state machine. What are we doing here? If we're ever doing a read tick or a write tick in mode 0, okay, this is the only time you use mode 0 is to write data into the VRAM or read data from the VRAM. And every time you do that, you want to advance your address counter. So this is the only way we advance our address counter. And remember, that's this register that's sitting down here in this diagram, all right? This thingy here goes into this mux, and over here, this mux is used to say, I want to read from the pattern table or the name table, the color table, or the sprite attribute, whatever. One of the inputs to this mux is the address counter, and it's right now all we care about. And this is what governs our read address. It comes up here. So whenever I do a mode 0 read, I need to make sure that the address goes over here, bang, and get the value out of this thing. And then when that's done, I need to advance this counter. Same thing if there's a write address comes out of this thing here as well, but we don't care about the mux because there's only one thing that ever writes. So we can hook that up to the writes address side directly. And when we're done with the write tick, we advance the counter as well. So if you look in here, if read tick is currently true at the end of this cycle, oops, wrong line. If the reader or the write tick is true at the end of that cycle, right, that's when that's true and the next leading edge arrives, we want to advance the address counter, okay? Of course, we're in mode 0. That's true. All right. So if we're reading in mode 1, then that's a status register access. We already talked about that. Otherwise, we're on to the races down here. So how does this work? Well, we take into account the state of our address of our addressing mode, or whatever you want to call it, the address state. And by that I mean the thing that remembers whether we're waiting for byte 1 or byte 2. Okay? If it's 0, we're waiting for byte 1. Okay? And if if we see a write in mode 1 at that time, then we know that we want to grab the least significant byte from the DN, from the CPU, and store it, because after the next write in mode 1, we need to store it in our counter. Okay, we'll see that down there in a second. So what else is going on here? Address state next is 1. So once we stick the least significant byte down there, we need to remember that if another mode 1 write comes along, we want to come down here and finish it, okay? So if there's another cycle and we come through here, what do we got? Another mode 1 write. We then set the state back to 0, because if we're going to do it again, obviously we need to start over again and set to the address from the beginning. We're also going to ask if D7 of the input is 0. Okay, that's the part that's asking, make sure this bit up here is a 0. Do not store this value in my memory counter register unless this guy here is a 0. And that's the true. That's true if we're getting ready to do a read from VRAM or a write. It's always 0 here, and it's a 1 if we're getting ready to store something into the VDP registers, the config regs, okay? So I didn't use both of the bits because I have only one address counter. So as long as it's 0 here on the second, access in mode 1, then we want to update our current counter value. And the most significant bits come from the data bus here, and the least significant bits were the ones we cached up here from before in this other register, this temp adder reg that exists for no other purpose than to hold the value in case we need it down here to put it in the register. All right, now this is going to happen. We're going to see stuff. We're going to come in here, and we're going to store stuff in this register, and that's going to happen every time the CPU wants to write into one of the VDP config registers, because it will do this in this guy's state 0. But when it comes down here and it's doing its second access to a VDP register, it won't come down here because that'll be a 1. And as I look at this and think out loud, I'm not sure this is right. Because if that's true, we do want to go, oh yeah, it does, okay. That's why this is up here, not inside this if down there. Okay, keep in mind, if we do this unnecessarily because the CPU is about to write something into the registers instead of into here, and then it does another one, which is what it does if it's going to store something in a register, like this, double mode 1 write, like this, okay? If that is happening, we still set our state back to 0. That's what I stuttered on. I'm like, wait a minute, is this in the right spot? And the answer is yes. I've been using this code a lot, so I know it works. But for a minute, I forgot why. It works because I don't do this until after I've reset my state for the next time. I say if and only if this second mode 1 write is supposed to be for my address counter to it. But I, no matter what, set my state back to 0. And the same logic you'll see in the register interface logic. I think over there I implemented a different style, just to keep the reader on their toes. Where's my register interface? I probably should unify these and make them the same. Arguably, this is a lot simpler logic here. There's the one for this guy. The memory counter, though, has a few other things to deal with. What's going on here? How do we do when I read the status register? He goes read tick. Well, this has a different set of ports and things like that. Yeah, this is only going to happen during a mode 1 access. Yeah, the ports work differently on here, so that's why that logic is a little bit different. But ultimately, in the end, if you look at what's happening up here in the top view that instantiates the register interface and the VRAM, these are hooked into this higher level module a little bit differently. Okay, and that's why my point is that's why the state machines work a little bit differently. Now, there is this thing here, this demux is the thing I foreshadowed. We can talk about that in another video. That's this register down here and that mux over there that has to do with how we read, how we get what we want, that's been gratuitously pre-read and cached down here. So I'll leave that as a foreshadow if you want to work ahead and look at the code in here and figure that out. What was I looking for? I was looking for the VRAM test bench, which is right here. So this will let us try this stuff out. What do we got in here? We just simply, we instantiate it, and then we run through a bunch of clocks, and what are we doing here? We reset it, and then I'm going to go through a cycle here where I set the, what I'm going to do, when it looks like I'm playing around here and a couple of different test patterns and stuff like that. What I'm going to do is I'm going to fill up the VRAM memory so that I can read it after the fact and have known values in there, because otherwise the waveforms show up red because they're all X, they're unknown until I make them known by writing something into it. So that's what's going on in this for loop. We go around and around, we do all but the last byte. And I do this just for fun so that we can see that, you know, when we go back and read it, that one of the bytes is not currently valid, just to confirm the test case that everything got put where it's supposed to go. So what do we got here? We're going to go into a mode 0, and then we're going to set the data in, and we're going to write this. What am I doing? Writing that in mode 0. Oh, it's because I already did the mode 1 stuff up here. I scrolled ahead too far. So what do I do here? I got a mode 1 write with 0. And I do a write tick. Okay, so that's going to set the least significant byte. We just look at the state machine. Then what do? We write, we turn off the write tick signal. This is a pause, a gratuitous pause, just to make sure that I can have multiple clocks in here between these two things. We'll see that in the waveform. So you'll see a pulse, and then it'll be idle, and then you'll see another pulse. You can remove this and it should work just as well either way, even if these are back-to-back, which I would argue is an absolute impossibility with our Z80, even running it at a super fast speed like 25 megahertz, because the Z80 takes many clock periods to finish any individual instruction, and this is going to be an out instruction followed by another out instruction from the CPU in order to create these two mode 1 writes using the output instruction. So many a clock will actually be idle between these two things when we run it on the real CPU. Okay, so I want to make sure it works if it goes idle in between is my point. So then we got another mode 1, which is a 40, which is the address is ultimately all zeros, and the hex 4 over here sets that second to top bit. Why did I do a 40? That actually is the pattern for reading, not writing. Where is it here? Oh, I read the wrong thing. That's this thing. If I put all zeros here, and I put all zeros for these address bits, and then I set this, that's a 40 in hex, okay? Followed then by multiple write operations in mode 0, okay? So that's what we saw in the for loop, right? So this sets up my address, and it gratuitously puts a pause between each of these write ticks and the subsequent, what are we doing here? The subsequent write ticks that are going to send all the data in there. So it looks like I'm going to do that down there as well. I'm going to do a single tick. I'm going to write what? And I ended with this. And that's because I want to know that I'm getting the right bytes out of the video memory. So what am I doing? I'm storing the low 8 bits of the address of the VRAM location. I'm storing that into the VRAM. That's what I'm doing in here. So byte at address 0 will have the value of 0. The byte at address, 10 in hex will be 10. if I have a byte stored at F10, I mean, I can only store one byte in there. I got a 1, it'll be a 10. So it's the least significant 8 bits of the address is actually getting stored into the actual data. That way I can recognize whether I'm getting the right byte out of it or not, okay? And then I'm going to just go through and generate a bunch of writes to fill up the VRAM, except for the last byte there. Between each one of these, again, I'm going to put a gratuitous pause in here that's not super duper necessary. And then some. I got another pause edge. I'm going to do a double wait and then come around and write another byte and so on, okay? After that, I'm going to wait a long time, and I do this so that I can find a gap on the waveform diagram to make it easy to see. What else? Wait and see the read ahead getting from the next address. This may be X. Yeah, so I put a note in here because if you use this, remember it's going to end 1 early. And I'm only going up to 2 000 and hex for these tests. And that means if you use this for loop, it'll only go to 1 FFE. If you use this one, it'll end, because it's explicitly less than, it'll end at 1 FFF. And it'll fill in all the bytes up to 0 to 1 FFF. This one will only fill from 0 to 1 FFE. All right. And down here, I put a note and with a big pause, so that I can look and see if the very last one is in fact not set. Again, like to confirm that everything is copacetic. And then what are we doing here? We're going to go in and set an address for reading. And remember that this value for the read setup is all zeros. There's the write, and the read has these zeros up there. So that'll just be 000. For both halves. These are slammed back to back rather than having the pause in between like we saw above. So this will test, will my state machine work in the ludicrously fast mode, which will never happen in realsies, but it should, all right, to make sure that that's okay. Then we have a pause, and then we have an exaggerated delay. So again, I can find the, so I can look at what D out is. If it's what is in D out, if I have an extended idle period. Then what do? We go through and we read from 0 all the way up to 1 FFF. And the very last one should have a garbage data in it. And I put in a check in here to make sure that the 8-bit value we get out of D out comes from the I register. I put this in here because in this simulator that we're using, if this is not, well, I is an integer part of a code generator, and if I'm not comparing an 8-bit vector to another 8-bit vector, this may not really come out right. So I did I either was getting a warning or something like that. So somewhere I declare val8 as an 8-bit value right there. Okay, so I is not an 8-bit vector in Verilog, so I wanted to make sure that the lengths and the leading zeros and all that fun stuff is the same. That's why I do this assignment here. Then I get some debug printings. We can see what's going on. If you want to, we do a mode 1 read. We turn it back off. And then at this point in time, the value should be valid coming out of the VRAM. And I ask, is it what I expect? If it's not, I gripe. I waste another clock signal down here and go round and round and round. And basically write a bunch of stuff in, read a bunch of stuff back, make sure it's all the same. Then we'll talk about this in a minute when we come back. This checks some quasi-crazy cases, as well as what happens if the FSM wants to do a DMA access while the CPU wants to get in there at the same time. This will be easier to look at on a waveform, but these are a bunch of scenarios. I'll leave it as a task to the viewer to actually look at the code and map it back to the waveform. We'll just look at the waveform here in a minute and see what it... once you get there, you can just infer what we were testing, because you can see what's going on with the waveforms. Okay, what's going on here? Give me all these signals and append them on there. I'm going to move this over like this, get a little more on the screen. Okay, bird's eye view. Here's the whole thing. From far left over here, when we reset, come out of reset. Oh, these things readable, all right. So what do we got going on over here? We got the state next and the state register. So the next and the regs, we already talked about this when we're dealing with designing state machines. This is the output of the combinational circuit, and this is after the next clock leading edge as it propagates through. So you see these staggered things. You see it on the address counter as well. I guess I'll leave it up there. It doesn't hurt anything. We got plenty of vertical space. So what happens here? Here's the reset. Let me turn on my things. We can look at the waveform. When I select the row, here's the right ticker going along with its big gaps in between. Here's the data in from the would-be CPU. Okay, and I turn the data in off in my test bench because it'll be garbage between these times, or it'll chatter or float high impedance as it's shown here between the axes from the CPU. Actually, by the time we get D in here, it's gone over the clock domain, and it'll be in a latch. We talked about that before. So this will actually technically never be floating high Z. It should have been X. I should have put an X in the test bench instead of the Z, but Z also means X with regard to the test bench anyway, so I think we're okay. Maybe an oversight on my part, but it doesn't change the usefulness, the validity of the test case anyway. So what happens here? We got a mode 0. We got a mode 1 right here. And remember, this is the way you read these things. This thing goes high as a result of this leading edge elsewhere in the design. So what happens is this clock went up. After that, this became high, and it stays high and goes low after this goes high. So be careful how you read these waveforms. This is the setup time for that leading edge there. Okay? Just because it looks like it's high at the same time this one, it's not. Okay? This one goes up one infinitesimally small amount of time after the leading edge on the clock. All right? So this is true here. That's why this propagates to the state register is updated on this leading edge here and not this one over there. Why did it go from 0 to 1 here? It went from 0 to 1 after the leading edge of this clock from the combinational circuit that sees mode 1 go high, and therefore if it stays high on the next leading edge over here, then the state machine is supposed to propagate this thing here, the next signal here, into the register over there. The real latch is the reg. This thing over here is the output of a combinational circuit, okay? So what happens here? I put a 0 into, that would be that the register that holds the counter, the address register, okay? And here's our adder reg. Because it was 0 anyway, you don't see it changing its value. We then see the 4-0, which means here I want you to put that 0 and the pre-latch 0 you see up here into our address register counter, and you don't see it change because it already was 0. So that's fine. What I could have done is set adder reg. I should probably do that. This is not the best example. I mean, I'm not giving you bad advice here. We really should have put in, well, yes and no. The reason that the address counter was 0 is because, oops, that's the test bench. It's because in here, when we reset the circuit, I set it 0 here. Okay? What I could have done is set it to X. So let me go ahead, just for fun, right now. I'm not going to put this in GitHub, just to show you that this is what's happening here. HX. Okay, and I type make VRAM. And then I reload this diagram here. That's this guy here, right? So now what it's doing is it's saying set the address to garbage when I do a reset. So that's why you can now see when the actual address register flips to 0, when this is high on the leading edge here after this second write tick. Okay, so that's how it got set to 0. Yes, normally if you set it to 0 and it's already 0, then you don't see the action taking place. So anyway, we got subsequent write cycles going in here. It's all set up. The counter is going to count. That's why you see it going 0, 1, 2, 3 here. Every time there's a mode 0, okay? Mode 0 write of whatever this is, a 0, oops, into the current address counter value, which is 0, you see right here. And then we do it, we write a 1 into the address of 1 and a 2 and all this other fun stuff, okay? So it fills it all up until over here, and you'll see it stop 1 early. Whoa. 1 early because it's going to stop at 1 FFF, or FFE rather. And that's what we see me writing in an FE, and I never write anything into 1 FFF because the for loop that I explained earlier ends 1 early. I want to do that on purpose. So that no one ever sets the value in memory at address 1 FFF. Okay, just to have a unique, interesting test case, that's all. So what's coming out of the output during this time is garbage, nothing, okay? Because I never actually read anything yet from any address that's valid, because the code, what it's doing is it's always reading when it's not, it's always reading when it's not doing a DMA mode operation, and this thing is 0 the whole time. So it's always reading, but what it's reading is from an address that has not yet been written to. Once we write to it, we advance the address immediately, so it never gets a chance to read from an address that has valid data, which is why the D out is invalid this whole time until we get over here, right? So now what's going to happen here? I'm going to do a, I'm going to write, what have we got here? We got a write with mode 1, and this is 2 writes back to back, a double whammy right here, these 2 clock cycles. I'm writing a 0, and then I write another 0. Oops, the second 0 gets written right there. That's why you see it propagate to the address register right there. Okay, and possibly fast, 2 in a row, and it works. So now we have an address of 0 in our counter, and now every time there's a leading edge on our main clock, it will read from this address that you see up here, gratuitously, in case the CPU wants to consume that data, and we'll talk more about that in another video. This one's getting too long as it is. Okay, so what's happening here? Every time I do a read tick, you see the address advance, and every time the address advances, on the subsequent leading edge of a clock, we see the new data byte coming out, and the data bytes that come out have the values equal to the low order part of the address, which is what I put in there in the test pattern that I filled in. And you see that true all the way up through the end of this, and it reads all the way up to 2000 in hex, or rather than 1 FFFFF. And because I commented out the logic and prevented myself from ever writing into 1 FFF, this down here still has garbage in it. I did that on purpose to make sure that I got what I expected out of the VRAM. And yes, I expect garbage. I got garbage. Perfect. Okay? And of course, I read all the way up through 1 FFF, and I gave it the extra clock to do so, and it left the counter advancing to 0 here. Okay, that's why gratuitously it's going to continue reading, and we see the zeros coming back out of the data, out of the VRAM. So far, so good. Everything works. What's going on over here? These are a bunch of crazy cases. We're sneaking in and out of here, trying to do DMA accesses. Where's the DMA thingy in here? And yeah, that happens over here. You know, I want to be able to test what happens if I'm doing, you know, back-to-back accesses and running too fast, faster than the CPU ever would. Make sure everything works fine. So what's really going on here? If we look closely, what are we doing here? We're doing a write right here. We're going to write a mode 1 write, followed by a read mode 1. This is testing what happens if I read the status register between two mode 1 writes. So notice what happens in here. The state next goes from 0 to 1, and it's expecting the second half of an address to get going for, you know, the continued reading or writing or whatever we want to do with this thing, okay? But if somebody sneaks in and does a mode 1 read at that time to read the status register, we reset the state back to 0, but we don't change our counter up here. If we change the counter, it would have been set to this 99 value, okay? But instead, we access the status register. So we throw away that operation. The garbage stays in our temporary register down here because we didn't consume it. And then later on, we do 2 more writes in mode 1 right here, okay? Bang, followed by this other one over here. And we see the state going from 0 to 1. And we want to put a 1133 in there from the data. And that's what we got into the address counter there. And it'll gratuitously start reading. And we better get an 11 because that's what's stored in L addresses that end in 11. And we do. Then what do? We click off a couple of reads. We see this counter advancing to 12 and then to 13, exactly as it should. Then what are we doing? What's going on up here? Okay, here's our first DMA action. We're going to do back-to-back DMA operations, and we want to say what's in 1100. And I want to see it right now without any regard to the address counter. I don't want to disrupt the address counter. I just want to see what's in there. Well, that should be a 0 in the next clock after this leading edge, and that's what we see on D out. So this would be if the state machine wants to, I want to see this, just do it really quick for me. It temporarily puts that on the output bus because it's told to. It takes precedence over the regular reading. And because it stays on, he can then move on to the next address, which is why you see an 01 here. It does it again, and you see the 02 there. And then the DMA read request goes off, and you see it falling back to a 13 again over here. All right? Now, we also put the read tick on in this cycle. Now, notice that when I do a read tick here, you see the address advance over here. That's fine, because in this cycle, that address is 13 in this example, which is why you see 13 right there. It's not until the next leading edge over here that the value from this address 14 comes out, and that's what we got. And at that time, we advanced to 15. And while this is all going on, it looks like we throw in another DMA read request from address 1103, which is why we see the 03 here. And then nothing's going on, and therefore, what does it do? It'll gratuitously read in case the CPU wants to see this 15 subsequently. All right? This is what's going on. Now, short of it is, this read tick here, while it's viable, and it makes sense in the context of what we built here, this one down here is kind of useless. And the CPU should never do this. We should never allow ourselves to do this. And as I said before, the CPU can never read 2 in a row this fast ever. And because the 13 was read way over here, even if you did want to do 2 in a row like this, okay, this 13 gratuitously was read in advance and would have been stored in this register down here when we look at the other parts of the design. In a video that's not as long as this one, hopefully, it would have been viable. Okay, this one over here simply moves on and says, give me the next one, and the results show up in the next cycle. I mean, theoretically, if you use this correctly, that could be useful. It's impossible because the CPU will never do this. But all of this stuff that happens as a result of it would make sense and is viable as shown here, okay? All right, so what do we got going on down there? We throw in another DMA operation on its own, and you see this go from 15 back to 15. Then we see a read tick. We consume the 15, and we advance to 16, but this happens at the same time as a DMA operation, which is why you see this move on to the 8, which matches that address, and because we're not DMAing anymore, the value from 16 comes out and is gratuitously read, and so on. And then we see what over here, we have a bunch of DMAs with a read in the middle of 3 DMAs in a row, and this was done for the purposes of making sure the address counter does in fact advance if you end up with an access pattern like this where the FSM reads 3 in a row and the CPU consumes, as we'll see later on, the advance 16 that came out here and is stored in that cache register. As long as the CPU doesn't try to read, more than 1 in a row before the FSM gets out of the way, and the read ahead gives you the 17 that comes from the address of the counter. So the next time you do a read should be at its soonest, like right here. Okay, and it turns out that, again, the Z80 cannot do 2 input instructions this close together. Because remember, this is a 25 megahertz clock, and the even the Z80 that has faster compressed instructions over the old original Z80, they still take several more than 3 clock periods to do an input operation or an output operation. So this is practical, useful, and that's why I built it this way. And we'll see how this gets used as we move forward. But I wanted to make sure everybody gets a good understanding of that. Otherwise, not very long, but somewhat subtle code. All right, so that's how the VRAM is implemented. We'll see how it gets used next time. Thanks for watching. I'll see you then.